Hello, team. I have a strong feeling I'm live now. So let's see how this goes. Hello, Kate, Jason, Beatrice, John. I hope you're doing well, and I can see more people coming online. So, today I wanted to have a conversation about basic differentiation. So, differentiation for us, yes, first principles is really important, but basic differentiation is sort of just a recap of what we did in level 2 and then trying to build on it. Okay? Afternoon, Oliver. So, basic differentiation involves a bit of review of level 2 and some building on. Can you hear me? Am I loud enough? Please just confirm this for me. Alright, so without too much further ado, let's start doing some notation. Okay, we started with this yesterday. So here's something. F of x denotes function of f of x rather. Okay. Subsequently, you could continue to use f of x, then g of x, then h of x, and so on as other functions of x. Right? F is the first letter we use because it denotes function, and the rest is because it's just really general. So from here on out, I will refer to functions as f of x, g of x, h of x, and so on, depending on what I feel like. Sometimes I might do a specific one. So I might do p of x. Okay, p of x in this situation is typically a polynomial of x. Right? So sometimes they're really specific. So typically when I use p of x, I mean a polynomial. Your teacher may have used this when teaching you algebraic long division or factor theorem or remainder theorem. They use polynomials quite specifically. But some letters you wouldn't use. You wouldn't use x of x or y of x. Or you might use y of x, but it's a bit weird. But you wouldn't use z of x too very often. Okay? So, that's function. Then we have this notation. F dash of x. F dashed of x or f prime of x is the derivative of the function of x. So sometimes we call it f dashed or f prime if you feel that, or f dash, I don't know, some people. And so all of these are ways of calling the derivative. The derivative, okay, maybe we should define the derivative. The derivative is the gradient function. Okay. Now the gradient changes. Okay, that's what that function is. Okay, sometimes instead of derivative, I might use the word differential, and I kind of mean the same thing. They're kind of interchangeable, differential derivatives, depending on what you're trying to do. Okay? Then, I also have y. Y is a typical function of x. But sometimes not. And so I stop using y. Okay? I don't use it as often. Once again, dy over dx. Once again, from the other day, it's the change in y over the change in x, where d is little delta, because it's looking at the little change in y over the little change in x. Very small changes in y and changes in x, that is why it's a gradient function. Because the smaller the change in y and the smaller the change in x, then the more accurate your gradient is. Okay? So, the gradient function. And we say this dy by dx. Sometimes we might just say dy dx, but we typically mean dy by dx. One more bit of notation, y dash. Informal gradient notation. Okay? I think y dash is the most informal form of notation that we use. I don't like it very much because I think it's some sort of, combination of these two. So these functions, this notation is called Leibniz notation, and I'm going to spell this wrong. So I'm going to just search it up really quickly. There's two famous mathematicians, Leibniz and Newton, and Leibniz is spelt. So all of this is called Leibniz notation when you use dy by dx kind of situation. Whereas up here, this kind of functional notation is called Newton's notation or functional notation. Right? Newton and Leibniz were really famous, people. I don't want to just restrict them to mathematicians, but they are mathematicians. They're also physicists, they're scientists, they're inventors, they're all sorts of everything. So Leibniz notation and Newton's notation both have their own place. You will typically see me using Newton's notation until later on this year when I start using Leibniz notation. I quite prefer Leibniz notation, but only after I've used Newton's notation for a long time. Okay, so basic differentiation. Nope, I spelled that wrong. Of polynomials. Okay, this is what we did in level 2. Basic differentiation of polynomials. Okay, consider p of x, see I've written as a polynomial, equals x squared plus 2x. Okay. We learned a very simple trick. And I'm going to write it in my words. It is, to find p dash of x, or the derivative. Okay, and this is, in my words, multiply by the power, then take 1 off of the power. Multiply by the power, take 1 off of the power. You don't need this of. Sometimes you don't say it, but I was going to be good English, but whatever. All right, multiply by the power, take 1 off the power. That is how we did basic differentiation. Let's try it. The derivative of this, for each term, multiply by the power. So the power here is 2, so x squared becomes 2x because I've multiplied by the power, and 2 minus 1 is 1. And then the power here was 1, so multiply by the power, so it's just 2x to the power of 0, and we sort of skip that and we write this is just 2x and this is just 2. And that is how we differentiate. And so we typically skip this step because it's a little unnecessary. You differentiate something squared, it becomes just x. If you differentiate something with an x on it, it goes away. All right. So let's try a few, and then we'll expand this. So question 1, f of x equals, I'm going to write if f of x equals 3x squared plus 7x, what's f prime of x? So you guys can do this and type this into the chat, that'd be awesome. 2. And this is remember, this is just a bit of level 2 stuff, so you guys should be fairly comfortable with it. Well done, Eddie. Yep. So question 3. Maybe I need to write them faster. Do them quite quick. F of x equals x to the power of 1 over 2. What is that going to be? Question 4. F of x is equal to x to the power of 4/5. What's that going to be? That's x. See if you can figure that out. So 3x there. Yep, first 2 are correct. Well done. I'm going to write 2 more questions for you. Three x to the power of 2/3 plus x to the power of 1/2. And 6 is f of x equals x to the power of -3. Okay. So I'm going to write these answers in, and I want to see something really interesting. So this one, 6x plus 7. This one, 2x plus 4. Don't, guys. f dash of x multiplied by powers, that's 4/5. Take 1 off 4/5. 4/5 minus 1 is negative 1/5. Okay, and I reckon that's very manageable to do, especially with you guys being able to do fractions. And this is 3. Eddie, yeah, just check your answer. There should be a negative somewhere. Okay. So team, what about these ones? So these powers might have fractions in them, but that shouldn't change how we go about it. So f dash of x, 2/3 times 3, that's just 2. And then 2/3 take away 1 is negative 1/3. Similarly, you multiply by half, and you take 1 off half, so negative half. Okay. Guys, I'm getting a lot from Eddie. The rest of you, what's going on? F dash of x. What happens if it's a negative power? Multiply by negative 3, take 1 off the power. Negative 3 minus 1 is negative 4. Okay. I'm going to pause there for a sec, and I'm going to ask the question, are these all polynomials? Oh, Eddie, you've got some nice fraction-looking things. Nice. Okay, can I just get a show of, comments? Do you all feel okay with these answers, or have I gone a bit too fast? Okay. I'm going to go and answer. Is this a polynomial? Yes. Is this a polynomial? Yes. Is this a polynomial? No. Okay, is this a polynomial? No. Polynomials can only have positive or integer-based powers, right? And so these ones are fractions, and so they don't count as polynomials. And so that's why I didn't write p of x for these. And polynomials also can't have negative powers. And so these are not polynomials. The top 2 are polynomials, the bottom 4 are not polynomials, but they follow the same rule as what we did in level 2. And that's why I've sort of just clumped them in here without giving you too much more explanation, right? Because it's just fractions, and fractions are your friends, and you can deal with them. All right, and this is basic differentiation. Now, if there's powers, if there's fractions, you'll be able to do some wild stuff. Now, I'm going to just ask 2 more questions, and this time I'm going to make them a little bit more awkward. Question 7, f of x equals 2 over x squared. So a polynomial function has positive powers of x with coefficients. So that's a plus bx plus c. Oh, I shouldn't be using a. You guys are going to not be happy with that. Polynomials, I don't know. Things that look like this. Where there's only positive powers of x. Right? Positive integer powers of x. So any combination of these. This is a polynomial. This is a polynomial. Right? All of those can be polynomials. But if there's a fraction or a negative power, then it stops being polynomial. Yep. So going back to question 7. Question 7 is real interesting because you can't just differentiate it like this. what you've got to do is you've got to rewrite this as 2x to the negative 2. Once you've done that, then you can differentiate. So now that I've written this power as a negative power, that's why we did that in algebra last year. Now you can multiply by the power. So when you differentiate, multiply the power, so that's -4, and take 1 off the power. -4 to the -4x to the -3. You could write this like this, but I don't mind negative powers, and so I'm going to just leave them as negative powers for now. Alright? Now, how could I make these questions harder? Well, I could add a whole bunch of them together. So I could do x squared plus 3x cubed plus 1 over x squared plus 4 over x to the 7. Right? Am I asking you to do that? Yes. But do you think it makes it harder? Do I think it makes it harder? I don't think so. I could put fractions and negatives in the powers, but I don't think that makes a difference in how the maths is done. So I'm going to leave that there. And if you guys want to answer it, you can. But I'm also conscious of the fact that it's not going to make much of a difference. Because I want to ask some interesting questions. If adding more terms doesn't make it any harder, what will? Okay. So anyone got this answer? I'll just write it out just in case you want to look at it. I don't expect you to have done this, but multiply the power, take 1 off the power, so this is -2x to the -3. Multiply the power, take 1 off the power, -28 x to the -8, if you got that. But if not, check in with me. Right? But the question is, what will make it harder? Okay, I'll just leave that there for a second. Okay. Here's a question. F of x equals x plus 1 squared. More letters, Oliver. Find f dash of x. Okay, so if you know the answer to this, that's good. But I want you to sort of think of what maths can you do to do this question. What would you do? Okay, I've not heard, but some of you may have said expand. Right? And I can expand. So, why not? I have algebra. This is x squared plus 2x plus 1. That's nice. And multiply the brackets by 2. That's where we're going to go. But, Kate, yeah, there we go. So, expand. So, some of you have said expand. Right? So, if I expand and then I differentiate, this is my answer. X plus 2. Right? That's pretty exciting. So, Lucy, let's try your way. Okay. Does it work? So, Lucy's like, Mr. Dharma, can you just go multiply by the power, and take 1 off the power. Isn't that what our rule was? And in fact, if you look, that's the same. But does it always work, Lucy? Okay, I'll give you one more. No. I don't know how to get rid of this. No, there we go. Try this. F of x equals 2x plus 1. Some of you expand, others of you do the Lucy method, and see what you get. Are they the same? I'll just put 2 copies here, so when we eventually do it, I'll do it next to each other. Probably not is the right answer. So have a go. So I'm going to expand here. F of x is equal to 4x squared plus 4x plus 1. And the derivative is equal to 8x plus 4. And then over here, I'm going to just do the Lucy, and I'm going to multiply by 2 and take 1 off the power. Now, is this and this the same thing? And no. So that one's wrong, and this one's correct. So, is expanding the best way to do it? Try this. What about this? Can I change that one? How would you do these? Is expanding still the best method? I'm going to give you about 30 seconds to decide whether you want to expand it. And if you do want to expand it, comment, let's expand. And if you don't, say why expanding would be a terrible idea. Yeah, so Oliver, you've dropped in some interesting words. I'm not going to use that word just yet. And Jason and Eddie and Charlotte, yeah, you don't want to expand 30 brackets. That's just not how. Can you keep it factorized like that? Well, the problem is we tried that for the one before, Lucy, and when we tried it for the one before, it didn't turn out right. Right? For the one before, the green and the blue didn't match. And so I think we can confidently say that's not okay. You can't do what you said, unfortunately, because it didn't come out with the right answer. If it did, then we'd do it. That'd be the way I would go about doing it. Even check the question, try it your way, and then expand it and see if it does. Okay, and because of that, I'm going to have to try and tell us that we've got to amend some of the learning that we've done. Okay, and if you kind of look, the difference between the green and the blue is it's missing a factor of 2. Hey, I'm a poet. Yo, guys, the difference between the green and the blue is a factor of 2. Okay, I'm going to stop now. So, what you can do, and what's kind of how people do, is for this green one here, for this one here, it will work, Lucy, but for this one, it won't work. And the reason being is because there's one small step missing. And I'm going to go to the top and tell you what it is. Multiply by the power and take one off the power. Off of the power. I am going to add something to this. Then multiply by the derivative of the inside. Okay, this addition is a really cool part of maths. We will in the future learn it as the chain rule, possibly, but for now I'm going to call it the bracket rule. Okay, but whenever you multiply by the power, multiply by the power, take one off the power, then you multiply by the derivative of the inside, whatever the inside of the brackets is. So let's try it and see if it works. And what we're going to try it with is this part here in green. So let's see if we can change our fate. Multiplied by the power, so multiplied by 2, took 1 off the power, so that's 1, and then I multiply by the derivative of the inside. And what's the derivative of 2x plus 1? It's 2. And so if I multiplied this by 2, I don't like using time symbols as multiply. I like using a dot. So from now on, if you see a dot, it's me multiplying, okay? And hey, this one and that one match. And so it works. And so, Lucy, there's some merit to this madness. So check it. This left one, the derivative of this is multiply by the power, take 1 off the power. I'm sorry, this is meant to be in some other color. Right? Multiply by the power, take 1 off the power, then multiply by the derivative of the inside. And the derivative of the inside is 1. And because of that, this would work without us having done that. You know, because if I'd expanded this, you know, just for those people who want expanding, this is x cubed plus 3x squared plus 3x plus 1. If I get 3x squared plus 6x plus 3, which is equal to 3 times x squared plus 2x plus 1, which is 3 times x squared plus x times x plus 1 squared. So in fact, it's a coincidence that this one worked without our new rule. Okay. So this one and this one is fine, but let's try this one here. I'm not going to expand 30 times, so let's try find the derivative. multiply by the power, take 1 off the power, then multiply by the derivative of the inside. And the derivative of the inside is, what is the derivative of 2x plus 1? It's just 2. And so my final answer, 30 times 2 is 60. 2x, 29. And that is crazy. Now you can do a whole bunch of crazy questions without actually having to do too much maths. Try these. Let's go. Are we going to do 100 brackets? What about this one? 6x minus 4 to the power of 200. Can you do these? And if you can, what about something slightly harder? What can you do? Give it a go. Try these and comment once you're done. I'm going to give you 2 minutes. In the meanwhile, I will tell you about why this is so powerful. This I'm going to call the bracket rule. In the future, we will learn it as the chain rule, but there's a bit more notation. Remember I said I wanted to do stuff in Newton's notation before we learnt Leibniz notation? And so that's why I'm not calling it chain rule. So people like Oliver, you've said chain rule. I think there's a bit more nuance before we can call it the chain rule. Eddie, I like that, yeah. Let's just see how other people go as well, okay? It looks really good. Yeah, so sometimes in calculus, what we can do is we can build on what we've learned in the last few last few years, and then change a few things. So like that little chant at the start where it was multiply by the power, take 1 off the power. Now we've added and multiply by the derivative of the inside. It's a bit of a mouthful, but it will work. It will always work for us. And yeah, Oliver, I like that. You've simplified a bit more than I would have. But here we go. Let's drop these. Multiply by the power. Take 1 off the power. Multiply by the derivative of the inside. Okay, you can actually leave these here. You don't have to simplify. Sometimes it's good to simplify. But typically the question will say you don't have to simplify your answer. So I want you to check these against your working and see if you got it. Multiply by the power. Take 1 off the power. Multiply by the derivative of the inside. And don't be foolish and try to expand again. It just doesn't make sense. Yeah. So this one here, multiply by the power, take 1 off the power, multiply by the derivative of the inside, which is 2x, right? And so now you have 40x x squared plus 1 to the power of 19, which is wild. I'm going to actually just move this up a little bit, team, so that I can... Alright, and then say with this one, or maybe down. That was an accident. Right, and so then the derivative of this, let's just check. Multiply by the power, take 1 off the power, multiply by the derivative of the inside, and the derivative of the inside is 2x plus 2. I would probably leave it like that. I wouldn't expand it any further, because I think it's ugly to expand it any further. But you could do what Oliver's done and write this, but I don't think this is necessarily any prettier than before. And so, with very small algebraic steps, I've now been able to differentiate some hardcore looking things. And so, I want you to give these a go. So this is basic differentiation and a bit of chain rule, not chain rule, bracket rule. I don't want to call it chain rule because there's a lot more to use, a lot more to understand before we call it that. So I'm going to call it the bracket rule. Really important. Multiply by the power, take 1 off the power, multiply by the derivative of the inside. And it will work for most cases, almost all cases. But there's a few more things we need to learn. So in our live stream next week, we will be learning how to differentiate some functions. So we'll be looking at exponentials, logs, trigonometric functions, and a whole bunch of them. And, it should be quite exciting. I don't have much more to do here. Your teacher will provide you with questions that you should be looking at. But I wouldn't stress. I think there's not much more to it. There's a few, doozies by the fact that you've got negatives in the power. But I don't think that should make much of a difference. So, I don't know. Just try one more. F of x is equal to 2x squared plus 1 to the power of negative 20. What's that going to be? Well, you multiply by the power, so now that you have negative 20 at the front, take 1 off the power, negative 21, and you multiply the derivative of the inside, which is 4x. And so if you simplify it, you'll get negative 80x, 2x squared plus 1 to negative 21. Boom. Done. Alright, are there any questions? Otherwise, I am going to end this call here. Hopefully this was illuminating for you. Hopefully I didn't go too fast. But I really want you to practice with fractions and negatives, and I think you will be able to progress into the next little bit. Thank you, Kate. Alright. And if there are no questions, I will call it a day. You're welcome, Jason. You're very welcome. Alright, team. I think that's a wrap. You're welcome, guys. Awesome stuff. Bye for now.